Hello everyone, this is Reza Gadusian from the University of Texas at Arlington. I'm going to demonstrate a foundation to track and classify vehicles on the street using OpenCV and Python. Let me just bring this up at first that this method is just a foundation, so it prepares the platform for other people to build upon this, and there is no claim regarding its accuracy. First and foremost, I want to tell you about the dataset that I use in this video. I use this website's dataset. This website is for a competition, a wide competition on tracking and detecting vehicles using different angles and video qualities, as well as having an unstable camera which vibrates from time to time. As you can see on your screen, these are all sets of input videos that could be used, and I used two of them in particular to train my model. So let's go to the program. I'm going to give you a little bit of instruction on how to run my program. First you have to run this first cell to make sure that it compiles and runs some few functions that I've written. And after that, we'll jump into the next cell, which is the main one. Here you can see the path to the directory in which I've stored my input video. After that, we got three important parameters that we need to set. First is a Boolean value parameter, false or true. When it's true, it means that we're on the training mode. So we want to operate on the training mode first, so we true this value. Besides, I've used k-means and PCA to classify vehicles because it's already been used in literature, and this variable k represents the number of principal components, which ranges from 1 to 326 or any other number, but in this case it could be 326. It's the total number of training images in general. I've picked it to be 100, and this is the number of clusters. 3 denotes vans, sedans, and big trucks. Well, it could range from 1 to any number you want, but the lower it is, the more stable results you get. So I'll run this program, I'll get a video, and I expect to draw bounding boxes around the detected cars and count the number of vehicles across a virtual line. Okay, here you can see in the top left corner the number of the cars that pass this green line, and that it's incrementing over time. You can see 7, 8, and these red bounding boxes represent each detected car. Each bounding box has a center point. You can see, using optical flow, we track and predict the location of these centroids. And as these centroids cross this green line, we count them. Another important factor that you have to know about these red rectangular boxes is that these will be our stored training data. By this statement, I particularly mean that once I draw a red rectangular box around each vehicle, I store them somewhere in my memory, and then I train based on them. So it's not like that I use another set of car images from somewhere else and try to apply them to my own data. The way it works is it adjusts itself with the environment that the camera is working in. So we mount the camera, face it downwards, starts detecting the cars, drawing bounding boxes around them, and extracting them, training based on them, and then testing. Another important thing we have to know is that we only consider one side of the highway. As you can see, this side where cars move from left to the right and we omit the other side of the street. If you ever get bored of watching this, you can press Q and it will exit this window, and that's what I'm going to do now, because I don't want you guys to wait. And I'll press Q now and exits. You can read here, number of cars 51, it counted 51 up to that point. But if we had waited more, we would have gotten 65 if we had waited until the end of the video. And 268 is the number of the training images, the number of those bounding boxes. And if we had waited even more until the end of the video, we would have ended up to 326, the number that I told you earlier. And just very quickly, I'm going to show you some 15 samples. You can see here 15 samples of those training images that we built ourselves using our input video. So we get back to the code. We change only one parameter, the Boolean parameter, which sets our operation mode to false. We toggle the value. Now we run it again. We expect this to classify now using k-means and PCA. Now if you look at the top left corner of each bounding box, you see a number which represents the cluster which that vehicle belongs to. You can see 0 represents sedan in this case. So if you see 0, it means that that vehicle is a sedan. If you see 2, it means it's a van, as seen in that white van. You can see 0 again. It means it's a sedan. 0 again, sedan. It doesn't work so perfectly as expected, so sometimes you may end up seeing other vehicles having wrong labels. Another thing that you have to take care of is that sometimes it just captures on some part of the asphalt instead of, or even instead of a single vehicle, or it sometimes includes more than a vehicle in a box. So the which is a proof to the shortcoming of background subtraction, and these are called garbage. I call them garbage inputs, so they have to be clustered differently. But for the time being, I just set the number of clusters to 3, so I don't include them. So we have to have vans, sedans, and big trucks. You can see here 2 again for this van. So if we have a van and it's labeled 2, it means correctly recognized. If we have a personal car, passenger car, it's labeled as 0, it means it's working correctly. You can see 0 here. Sometimes it doesn't work. If it's especially white, it doesn't work. Because regardless of the type of the car, if it's white, this groups it into the same cluster, unfortunately. So now again we press Q. I'm going to show you the pipeline, or the architecture of my model. Each frame is pre-processed or filtered through a Gaussian filter, and background subtraction is applied, followed by morphology. On the right side you can see the result of morphology, not the kind of morphology you expect, because this is the foundation for the rest of the work, and this could be only one of the reasons that the result is not the one that we expect, because I'm not going to brag about the accuracy, and I have no claim about that part. I just claim about how structured this method is, that you can literally replace one method like PCA with another method with little variations required and a little probability to violate the whole flow of the structure. So after that, we calculate the centroids, those little solid circles, and we track them to enumerate all the cars, and as well as storing those rectangular boxes known as regions of interest to build our data set and do PCA and k-means, and which eventually will result in classification. I'm going to go scroll down and show you the final results. So if we had waited until the end, we would have gotten 65 out of 70 of them counted, which is 92% accurate. Good, promising. But this is not the result. The result for classification is not comparable to the result for enumeration, as only 36 out of 57 total passenger SUV cars are correctly classified. Even this value is narrowed down to 3 out of 10 and 1 out of 3 respectively for van and big trucks. And total for, if you calculate the weighted average accuracy, it becomes 57%, which is not good. So way more room for improvement, but as I told you earlier, we've gathered enough information here that you can literally, after reading upon all of these, you can feel comfortable to work with them and just take one step further. Yeah, that's pretty much the whole story about what I did here. I hope you found it useful for yourself, and you can ask any questions if you think it was helpful. Hope you have a great time with your family and friends.